I know some people were still collecting. Some people were still collecting data over the lunch break or hadn't quite finished. There is the example data set available, which I put in this directory here. What I'll copy across the aggregate data as well into that directory. So let me get that into there and set it up just to make sure that everybody can read it. So if you haven't quite got to the stage of having the aggregated data set or collecting all the data, there's a full set of the data there for you. And I'll copy across the other one just for completeness. To make sure that everybody has the same set of data or has access to similar data, so we can move on. Before we do that, though, I want to check if there's anything that anybody thought about over the lunch break, or anything that wasn't clear to them, or they realised with reflection that they didn't quite understand, that people might have questions about. So, has anybody got anything they want some clarification on, or has a question they'd like answered before we move on further in the course? So Evgeny, you're asking the number of 3 runs as a minimum for the for benchmarking. So the reasoning behind that, in some sense, is it's not the ideal situation, but at least with 3 runs, you can have some sort of spread of data. Right. Oh yeah, could you check the 2-node 256 submission script, please? Yep, sure, of course. So Evgeny, that's not that I'd say that's the right thing to do. It's saying that it's probably the minimum if you can manage it. I did say during the course that also, you may, if you're running on very large core counts, you may even struggle to get up to 3 runs and to try things out a few times, and you may only be able to manage 1 run, or so the ideal is actually as many as you can manage, and ideally distributed across at different times in the day. No, thank you, Michael. So that's the S-run script for the 2 nodes of 256. So although 3 runs is not ideal, if you've managed to do 3 runs, then at least you have some sort of way of measuring the spread of performance that's maybe not ideal, but gives you some confidence, especially if they're all close together, that you're measuring something useful. Now, if you did 3 runs and the performance results and the timings were varied a lot, then I think that'd tell you that 3 runs wasn't enough, and you'd have to be doing something more careful to make sure you understood what the performance was and do something more statistical. Because if the performance is varying a lot, there's something underlying that, and you need to have a handle on what the level of variation was, right? Are they normally distributed in times? Do you get lots of very fast runs and the odd slow ones? You get lots of very slow runs and the odd fast one. You'd have to have more confidence. So I think if you did 3 runs and they're all close together, sorry, if you did 3 runs and they were all close together, then you've got some sort of confidence. But if there was large differences, then you might want to look more closely. Sorry, Helen's asking, in an earlier session, underpopulating nodes was discussed. Could we do the same thing in benchmark here too? So yes, and yes, it's what you've been doing, right? So when you've been doing the single node runs and you've been using less than 128 cores, you have been underpopulating the nodes. But yes, if you wanted to see the difference between, for example, 128 core, if there was any difference between an 128 core run using a single node and 128 core run that's around 64 cores on each node, you could do that as well. I'm sure one of the helpers could help me out by putting in the syntax for that in the job submission in the Etherpad. And the only thing you usually have to set as well is CPUs per task has to be equal to the stride between tasks, to distribute the cores evenly across the node. But it's a pretty simple change to make that happen. So at the moment, as we've been building up, we've been using all those nodes on one socket. That might not be ideal if you're running a full application and you want to access the memory across both sockets in some sort of uniform performance way. But for this small test case, it doesn't really matter. But yeah, so yes, so the extra consideration when you're underpopulating nodes is how you distribute the tasks across the node, whether you distribute them evenly across both of the processors or whether you load them all onto one processor. And there's different settings that allow you to do that. And if you want to know more about that, that's fine. We can we can put some stuff in the Etherpad to help you out, and I'm happy to chat about it at the end of the course. Okay, so hopefully everybody has access now to some version of the benchmark ag CSV file, either one you've created yourself from your own runs or the one you've taken from the example data. We're going to use this from now on to start to do our analysis. The first thing we're going to do is our aggregate data at the moment only contains the timings, and we want to also be able to compute the performance. So we're going to load load the data into Visi data again, and use the data in there to compute our performance metrics in megapixels per second. So let's do that. So VD benchmark ag.csv to get started. Okay, so here's my aggregated data with the minimum timings from each of the benchmark runs. Some of them, okay, so from each of the 3 benchmark runs at each time. Now we're going to compute a new column, which is the performance in megapixels per second. And this is the size of the input data, the size of the image in megapixels divided by the time for the calculation and for the overall one. So let's do it for the calculation one first. The way you do this is quite similar to Excel. If you're familiar with that, is you highlight the column you want to add the column to the right of, and we'll press equals to start making a formula, and then you give it the column names of what you want to compute. So we want to use size min, which is size underscore min, divided by calc min to get the calculation performance. Okay, and you can see it didn't quite work. So what did I do wrong here? Okay, what I've forgotten to do before I started was to set the numerical types of the columns in the spreadsheet. So I need to make sure that size min is a floating point and calc min is floating point, and then you'll see that it actually computes the performance because it knows how to divide 2 floating point numbers. While I'm remembering, I'm going to go and change overall min to a floating point one as well, and I'm going to change cause to integer data with hash. And we type % for floating point data in a column and hash or pound for integer data in a column. You can see it's included lots of decimal places, and it's assumed that these are floating point data. That's what these yellow percents mean. I can convert this column to explicitly be floating point data just by pressing %, and that'll tidy things up a bit. So you can see as the calculation time goes down, the performance increases. Okay, the name of our column is useful, but maybe we want a slightly different name. So we can change that. I just need to remember what I called it. So I want to make sure we give it the right name, calc perf max. Okay, so I'm going to use the up chevron. So that's this character here, and that allows me to rename the column. So I'm going to call it calc perf max. Okay. So now I've computed the performance in megapixels per second. Now, can you go ahead with your spreadsheet and do the same, do the equivalent process to calculate the overall performance as well? Okay, so it's in the same way, and rename it to be overall perf max in the same way as we did with the calc one. I'll give you a moment to do that before I go ahead and do it myself. else that one of the attendees pointed out to me earlier this morning. So when I talked about the things you could vary that might affect performance, we talked about number of processes, number of threads, input parameters to the program you're using and such like. And the one thing I forgot to mention, I hadn't really thought of course, is also the parameters to the job submission script as well, to the job submission script itself, or srun in our case. You notice that we have these two extra options on srun, the hint no multi-thread and the distribution block. The reason for those is if you just let Slurm do its default settings and its default way of putting things on compute nodes, you can actually get just much worse performance from some particular functions than you can if you specify those options. So as the person pointed out to me this morning, one of the other things you might want to test your benchmarking is the effect of different options to the batch system itself, as well as the other things we mentioned there. And what I'm going to do is I'll update the course material after this course to include that explicitly, but I just realized I'd forgotten to mention it at the time this morning. Okay, so most people seem to have managed that. So let me just fix my one up and get it right. So this is going to be, it's going to be size min over all min. And then I'm going to set it to floating point, and I'm going to change the name to overall perf max, like that. Okay, so now we have a spreadsheet with both the timing data and the performance data for the maximum value from the set of benchmarks we ran. So let's save that again as benchmark underscore perf, and save that as a different name again as benchmark underscore perf.csv. So remember, savings control S, and it's going to suggest the same name we had already, but I'm going to call this one benchmark perf.csv, press return. Okay, and then I'm going to quit out of VisiData again. Remember, it was GQ to get back to the command line. And I should now have the three different benchmark CSV files. I'm going to copy it across to the shared data place, just shared data slot, just so everybody's got access to it in case they didn't quite get that far. Okay. So again, there's this small test that we usually, this small exercise we usually do to get people chatting to each other, get people warmed up after lunch. Again, we're talking about why you might want to use benchmarking. Having seen what you've seen so far, thinking about your use of HPC, what would you want to get out of benchmarking applications, and think about what would you want to, which aggregation would you want, minimum, maximum, mean, performance variation. Why would that be appropriate for what you want to do, and why would it be appropriate? Oh, how do you delete a column? So you can use, just let me get the, so I'm not 100% sure, actually, and I could look at, I'd have to go and look up in the VisiData. I'd have to go look it up in the VisiData manual. Now, I think you could definitely use minus to hide a column. So if you highlight a column, hit minus, and that should hide the column like that. Now, when you save, I'm going to save it to t.csv so I can test whether that means that when you save the t.csv, it's gone. Let me have a quick look. Yes, it does. Okay. Thank you, Michael, for the VisiData cheat sheet. But you could use minus. It will get rid of the column, and then if you save, it's not saved in the saved data sheet. Okay. And what parameters would you be interested in varying for the application you want to benchmark? So I'm going to leave that as an exercise for you to think about following on the course. and how you want to use this material and the information you've gained today and the experience you've gained today going forward. But just to bear in mind, again, it's about thinking about what you want to do and planning out what you want to do. Now, I mentioned right at the start, right back at the start, that you may need to capture different details about the run that the application's not capturing. We've seen that the Sharpen application or the Sharpen program, along with the input, captures a number of useful things, which are the size of the input data, the timings for the calculations and the overall timing, and the number of MPI processes used for the calculation. They're all captured in there. But there may be, but the things it wasn't capturing, which we included, was the run number, which is unsurprising because it generally won't do that. So we had to append that already to our file names. And we did also use, you can see the number of cores here. Although that's contained in the output file, it was useful for us to help us see what data we had just by listing files. But again, depending on what you're doing, you might have to capture different things. So some concrete examples of scenarios and the types of data you might have to capture are the thing we're doing now, which is comparing performance as a function of number of cores or nodes on a particular HPC system. In this case, you need to ensure you've got the number of cores, nodes, MPI processes, OpenMP threads, depending on what's varying. Most applications include this somewhere in the output, though in some cases they don't, particularly with OpenMP threads. It can be more variable whether they capture that data or not. If you're comparing performance as input parameters change in your in the input to your application, you may need to make sure that the changes to those parameters are captured in the output of the application itself. In almost all cases, these should be, because most programs echo some sort of or summarize the settings for the input case in the output, where you should check that all the information is there. Now, comparing performance applications that are compiled in different ways, either using different compilers or different compiler flags, you need to somehow capture those sorts of things. And these aren't usually captured in the program itself, though some of them do let you set headings, which will be printed out in the output to specify what was used. But generally, you'll need to capture this yourself, either by storing different data sets in different appropriate labeled directories, or including something in the name of the output files that let you label these. And if you want to automate the analysis of them, you may need to capture something in the output file itself, in the output file name itself, in the output file itself. And comparing performance across different HPC systems, which is something we could do quite a lot of at EPCC, means that you need to capture all of the above, essentially, because the compilers will be different, the number of cores, number of cores per node will be different, so you can't assume those sort of things. And the other thing is that things like environment variables will be different, and the CPUs will be different, so you have to start thinking about how you capture those pieces of information as well, even if it's as simple as using something like LSCPU and outputting that to the file. So LSCPU gives you, for example, information on the processors that you're running on the system, and you can LSCPU and pipe the output into the output files to ensure you've captured it along with each job that you run. So with all the aspects we've discussed so far, it should give you enough information for you to be able to analyze what you want to gain from doing any benchmarking of your own use of HPC, and what details you need to capture, and be able to make a plan on how to do this when you collect the data. So that's the end of the section on collecting the benchmarking data. Hopefully you can think back, we talk about basic terminology, the difference between timing and performance measures, between timings and rates, and how you might combine those, selecting different performance metrics. In our case, we made up one here that was megapixels per second, because that seemed the most appropriate for the case we were looking at. How we run benchmark calculations and gather data, and we'll talk about that in a bit more detail later on this afternoon when we look at things like how you might automate collection to speed up things, because it was quite a manual process even for this small, simple case we were doing. And finally, we've touched on capturing information on the differences between different benchmark runs at the end. And we use this simple Sharpen example to allow us to collect the benchmark data. So the next step, now we have our data, is to actually analyze it in such a way that we can use it to make decisions about how we use HPC, and that's what we're going to go and move on to next. So while I'm skipping on, if anybody has any questions, please ask them about the stuff we've already covered. Otherwise, I'll crack straight on with the next bit of the course. Oh, of course, we did launch slightly out of sequence. Okay, I'm not seeing any questions right now. So let's move on. As I mentioned, in terms of analyzing performance, what we want to know is, what can we use from our benchmarking to actually start to make decisions, right? Because it's interesting collecting data, and you can look at the data and think, oh, it's interesting data. But actually, what you need to do is be able to use that data and turn it into information that you can make decisions based on. And in this section as well, we'll also have a look at what stops HPC applications from scaling up just to an arbitrary number of cores, MPI processes, threads, whatever you want to do, and what the limits to parallel scaling are. We'll briefly touch on that at the end of this section. So the first thing we're going to do is, it's all very well, you've seen we've got a CSV and some sort of spreadsheet of the data which we can use to do some sort of analysis, but you often want to actually have a look at the data. It's sometimes better summarized as a plot, and VisiData gives us a simple way to do that on the HPC system itself without exporting the data to somewhere else and putting it into a plotting program, and without having to worry about installing X windows and getting graphics working over the network connections to the HPC system and things like that. So what we'll do is we'll use VisiData again to load up our benchmark perf CSV files. Let's get that up. So DD benchmark perf.csv. Just give me a moment. I'm going to close the door to this room because my family have just returned. Okay, so we don't get disturbed. So here's our data again that we computed at the end of the last section. The first thing we're going to do is we need to again tell VisiData what type of data is each of the columns. Okay, and you need to do this each time, unlike Excel, which remembers the data types of columns, because the CSV doesn't contain that information. It's a very simple file format. So let's go ahead and do that. So cores are an integer, column size is floating point, and all the rest are floating point, and count I'm not really interested in because we're not going to plot it. Oh, in fact, sorry, I'm being silly. Let me undo that. So I'm going to change these ones back. If you ever set a column to a numerical data type by mistake and you want to remove it, and you'll see why you might want to do that before, you can use the tilde character to switch it back to a string. So I'm going to do that for the timings columns. So the only ones, and the size ones, the only ones I want to set are the cores to integer data and the performance columns to floating point data. The reason I'm doing this is because when it comes to plotting data, VisiData says, oh, I see numerical columns, I'll plot them. If they're not numeric columns, I won't bother to plot them. And I actually only want to plot the performance here in the first instance. I don't want to plot the timings. Okay. So we've got the two data sets we want to plot as numerical values, which is great. We've got the categorical data, which is the x-axis says type, but it needs to know which column to use as the categorical data. And you do that by marking it with an exclamation mark. So you go to the column you want to be the categorical data, the x-axis, and you press exclamation mark. You can see in my case that turns the column blue to indicate that that's what it's doing. And then, so we've now got something that looks like this. And then finally, we're going to graph this, which is we use the command G and then dot, a period or a full stop, whatever you want to call it. So not typed together, typed in sequence, G dot. Okay, this is quite hard to see on my screen, but hopefully it's clearer if you've got it plotted on your, because it's so small. It'll be clearer hopefully on your own terminal window. So you should be able to see two different colored lines made up by points. There's the red one, which is going along here out to 256 cores, and there's the green one, which is going up here. And the green one is the performance of the calculation part, of the application, and the red one is the performance, the overall performance of the application. You can see they're very, very different. In fact, what I've done in the thing here, because again it's hard to see when you see the output put into the screen, is I put it into Excel and plotted it in Excel as well. Just did a simple plot in Excel. So to look at it more clearly, this is cores along, but this is exactly the same plot, just plotted in Excel instead. You've got performance in megapixels per second up the side, and cores of the x-axis, and you can see this is the calculation part of the application. This is its performance, and this is the overall performance. Okay. Now, one thing I did want to show you is we can use busy data. Why did we plot the performance and not the timing data? Okay. So let me go back. So Q takes you back to the spreadsheet interface. Now this time I'm going to swap around the columns. So I'm going to put the calculation ones as numbers and the performance ones as strings. So I'm going to be plotting the timings. Sorry, I'm going to plot the timing, the minimum timings rather than the performance. Okay. So G dot to plot again. And this time you can see the data points here. So the red ones overall, here higher, and the green one, maybe hard for you to see, is the calculation performance, which is right down at the bottom here. Now, one of the reasons we plot performance, often plot performance rather than timing data, is that it's easier to see the difference and to interpret the differences between the performance rather than the timings, especially as you approach higher core counts where things just like they look like they're running in parallel, and it's hard to see differences in slopes of lines and differences in and what that means for the performance of your application. Okay, you could try plotting it in Excel. Hopefully it's a bit clearer on your terminal window for you to be able to see the plots themselves, because it's quite small. Yeah, I can see it's quite small here on the display, and they're quite difficult to see. But the performance, if you plot it, generally gives you a better view of the differences between the things you're comparing, rather than plotting timing, raw timings. That's just not to say plotting raw timings is wrong, but plotting performance can actually be more revealing. So I'm going to use Q to get back out of there again. So let's look at the plot here, which is easier for you to see on the web interface. What is this actually showing, right? So you see the performance of the calculation part. If you remember, there were two timings in our output, and that's what they were based on. We roll all the way back to when we first looked at the output of the sharpening example. It had two timings. It had an overall one, which was the calculation including reading the image and writing the image. And then there was the calculation part, which was the bit that just did the sharpening calculation. You can see there's a very different performance between just the calculation bit and the overall performance here. So can anybody think of any explanations about why they look so different? What the difference is here and where this is coming from before we look at the solution? I'd be interested to know if anybody's got any ideas. So other processes. So that could be true. So one of the things you've always got a chance of being affected with here, particularly on Archer, as we're running on a system that's shared by lots of other users, is there's always a chance that something somebody else is doing is affecting the performance of your application. In this case, I think that if it was affecting the performance of the application, though it's not quite true actually. It's more subtle. Yeah, you're right, Helen. It is more subtle than that. I was about to say you'd expect to see it affect. It would affect both the calculation and the overall performance, but that's not strictly true because of what the difference is due to. I'm being a bit cryptic because I don't want to give away the answer before people have had a chance to speculate. But it isn't one of the ways we try to mitigate that on ARCHER2 and Archer previously is that you can't share nodes with other people. You might get other processes running from the operating system that could potentially affect performance, but they shouldn't do that. There's something wrong with the node, with the compute node, if the operating system processes are affecting your performance in that much. Yeah. Okay. Sorry, Helen. I understand. Yes. You're exactly right then. Okay. So it's other things that are going on in the calculation. So the difference between the calculation part and the overall part is that the overall includes the I/O, includes the reading in the file and writing out the file. So what is actually going on here is that somehow that part of the program, the I/O part, the reading in the data and the writing out the data, or either one component of that or both of them, is causing the performance to be really poor, or the scaling to be really poor overall. Okay, whereas the calculation bit looks like it's doing quite well and has a lot of good performance even as you scale up to higher core counts. The I/O bit isn't. Okay, and that is hurting the overall performance. Okay, so it's exactly that. So, and what we'll do is a little bit later on in this section, we're going to look at the limits of parallel performance and scaling, and that'll play into this. And then in a couple of sections time where we look at profiling, we'll actually see what the I/O looks like and why and where this could be why this could be a problem, or another way of looking at why it's a problem. Okay, so that's all very useful. We've plotted data, we've got some idea, there's something different going on between the overall scaling and the calculation scaling, but we still haven't really got anything concrete to help us make decisions, right? So plotting data is useful and we can get a feeling for what it looks like. But what we want is quantifiable that we can use to make decisions about our use of HPC systems. And to do that, we eventually want a metric called the parallel efficiency. Okay. On the way to get to the parallel efficiency, we're going to calculate something called speed up. And that we use that to calculate the parallel efficiency. But let's have a go at that. So in fact, you can have a go at it. There's a small challenge here, right? It's using the data we've got, this Visi data here, which we were plotting before. I'm going to make all the columns numbers again. Let me do that. Okay. Can you calculate the speed up from the performance data you have? Now, remember, the speed up is the ratio of the performance to the baseline performance. And if you remember, our baseline was at 1 core. Okay, so so the first step is to compute the speed up for both the calculation and the overall things. Add columns to compute the speed up for calculation and the overall thing, and also add a column with values for the perfect speed up. Now, I think it was Jove asked earlier about what perfect scaling or perfect speed up is here. Now, because our baseline is on 1 core, and we start on 1 core, our speed up, our perfect speed up, is actually equal to just the number of cores. So if you have 2 cores, you would expect in the perfect scenario that your code would go twice as fast as the baseline on 1 core. If you had 4 cores, it would go 4 times as fast as the baseline 1 core. In a real benchmarking case where you're maybe not starting from a single node or for a single core, then your speed up is the ratio of the number of cores you're using to the number, or the number of nodes or cores you're using to the number of nodes or cores you used for your baseline. Okay, but because our baseline is 1, that ratio is just the number of cores. So can you go ahead and try and add those 3 columns into your spreadsheet? 1 with the perfect speed up or perfect scaling, 1 with the speed up of the calculation part, and 1 with the speed up of the overall part. I'll put up a little poll so people can tell me when they're done, and then we'll have a look at when they're done, or when they think they're done, and then we can have a look at the solution. If any of that's not clear, please let me know. Okay, right, let me show you how I did this on my spreadsheet, or how I can do this on my spreadsheet. and then we'll carry on. So let me go back to here. So the first thing I'm going to do is make a perfect scaling or a perfect speed up set. And that one's relatively simple because it's just the same as the number of cores. So I'm going to do equals to make an expression, and I'm just going to give it cores. Okay, and it creates a new column that's got the same number of cores. I give that a hash to make it numerical. I'm going to change its name using the up chevron to perfect speed up. Okay, so that gives me a column with the perfect speed up in, which is just the same as the number of cores. Then to get the speed up for the calculation, I use the calculation performance. Now I want to use it relative to my baseline. So my baseline performance is 0.15 on a single core. So I'm going to create a new one with an expression, and it's going to be calc perf max divided by 0.15. Okay, that divides every value in the calc perf max column by 1.5 and makes a new column. Okay, that's a numerical column. So I give it a percent, and I'm going to rename it as well and call it calc speed up. Okay, and then I'm going to do the same with the overall perf max. So I'm going to make a new column equals overall, oops, not coverall, overall perf max, and this time divided by the baseline for the overall performance, which is 0.14. And that's created a new column there. Ooh, did I do something wrong? Yes, I can't spell, is my problem. So let's get rid of that one. And let's try again. Equals. I spelled the name of the column wrong, is what I did wrong there. Almost did it again, 0.14. Overall perf max. Okay, that's better. It's actually got values in it this time. I set it percent, and that, I'm going to rename that one to be overall speed up. Okay. Now I want to put the other final thing I asked you to do was to plot the speed up and the perfect speed up. So I'm going to do that by, you can use minus to hide the columns if you want to stop them being plotted, but you can also use the tilde trick as well. So I'm just going to tilde all the ones I don't want to plot. Ah, yeah, that really is a problem. Maybe that doesn't work. So because it's computing the other values based on it. So I am going to have to use the minus trick here. So let's get rid of that one. Minus, 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 and minus. And then hopefully I should be able to plot all of those with just G dot. Okay, so there's 3 plots this time. You can see up in the top corner. There's a green one, a red one, and a yellow one. The yellow one is the overall speed up. The red one is the calculation speed up, and the green one is the perfect speed up. And you can see that the calculated one is much closer to perfect than the overall, which is sort of what we'd expect. So let's have a look at the solution. I think what I have here also is a Excel plot, which is easier to read over the screen, that shows how far away I was. So this is the overall speed up, the calculation speed up, and the perfect speed up. Okay, so you can see the calculation one is much closer, but it's still not scaling perfectly as we go up in core counts. So I am now going to I'm going to save this data as well. So let me get back to use Q to get back to the spreadsheet interface, and GV will G then V unhides all the columns that I hid, and then I'm going to save this one as well. So let's do a Control S, and we're going to call this one benchmark speedup.csv. Oh, that one I need to get rid of. Let's try that again. Sorry, that was me when I created the column with the wrong name. Benchmark speed up CSV. Okay. Okay, so I've now saved that data as well. I'm going to leave it open for the moment because the next bit's going to involve using Visi data anyway. So there's no point in me closing it and then reopening it because I'll just have to set up all the numerical types for the different columns. So does anybody have any questions on what we did there? We computed the speed up by dividing the performance by the baseline performance. Okay, that was all we did for the two different metrics we're looking at. So one of the things you might notice is there's not much difference between this plot, right? This plot. So what was the point of the first step? You mean the computing the performance or computing the speed up? The count. Oh, so that gave you the column that was the perfect speed up to plot. Okay, so in this case, it was equivalent to just the number of cores. Okay, but that's not generally true. Generally, the perfect speed up line will be the ratio of the number of nodes or the number of cores at the run to the number of nodes or cores at the baseline. It just so happens that our baseline in this case was at 1 core, so everything was divided by 1, so they were equivalent. Does that make sense? Yeah, so if your baseline was on 64 cores, the perfect speed up, the perfect speed up at 128 cores would have been 2, not 128. Because 2 times 64 is 128. Okay, but what you should notice is these plots look very similar. Apart from the addition of the perfect speed up line, the calc and overall speed up look very similar to the plot of calc performance and overall performance, right? There's hardly any difference between them. So why would you want to plot them both anyway? And actually, the answer is sometimes people use speed up when you want to look at, particularly when you want to compare it to the ideal speed up or the ideal scaling. It's useful to have the speed up data to be able to do that visually. It makes it much easier. Otherwise, you have to renormalize actually you have to recompute the ideal scaling, the ideal performance rather than just using the ideal speed up. Okay, but actually, it's really because it's a useful thing to compute on the way to computing the parallel efficiency, which is where we're going to go next, which is often the thing that you want to use to make decisions on your use of HPC. So plotting performance is generally better for showing differences between different setups because it avoids choosing a baseline that must be made when you're plotting speed up and gives a better indication. So usually if you want to show the difference between different runs, you'll plot performance rather than speed up. Speed up is only used to compare to ideal speed up and on the way to calculating parallel efficiency. Okay, so now we've got columns with the speed ups and the perfect speed up. We can use these to compute the parallel efficiency, right? And if you remember, the parallel efficiency is the ratio of the observed speed up to the perfect speed up. Okay, so it's the ratio of how well you're doing to how well you could potentially do. So let's go ahead and compute this. Okay, for both the calculation and the overall. Okay, so remember we've got the perfect speed up column, which we need here. Okay, and so we want to create a new column, which is the calc speed up over the perfect speed up. Okay, I'm going to put % there to get it formatted nicely. And we're going to do the same for the overall as well. So this is going to be over all speed up divided by perfect speed up. Okay, that's gone off the side, but I'm going to set that one to percentage as well. Okay, so let's ignore the calculated speed up for the moment. In fact, Just a minute. Let me rename those as well as calc efficiency. And this one's going to be overall efficiency. Okay, and I'm going to save that just in case things crash. I'm going to call it benchmark efficiency or benchmark EFF. Just so I've got a copy of it. Let's take a look at the overall efficiency here. Okay, as we increase the core count and go down. Does anybody have any suggestions for at what point, at what number of cores we think this stops scaling in a useful way? You know, so if we are trying to make a decision about how many cores to use for a calculation that made the calculation reasonably efficient, at what point do we think it stopped being useful? How many cores would you choose to use for if you were running this application in production based on these benchmarking results? Because it does continue to get faster and faster. So 2 to 4 cores, 8 cores, 32 cores. Any more for any more? 8. We've got 2 votes for 8. 4, 8. Okay, so 8's the popular. Evgeny's a bit more ambitious here. Okay, so you can think of these ratios can be expressed as percentages, which often makes it easier to think about, right? So this is 93% efficient, 79%, 62%. So it is subjective here, right? And it depends what your motivation is, and I'll talk about that in a moment. But I would think that 4 to 8 is looking like the right sort of limit here. You know, I think what people say, okay, Evgeny was looking at the calculation ones. Yeah. So the calculation are much more efficient. But generally, once your parallel efficiency is falling below 60%, then it's not really considered useful. If it falls below 70%, it's considered not ideal. So if you really wanted to push this one, you're talking 4 to 8 cores. You know, 4 is probably better in production because you're not wasting huge amounts, but you're getting a reasonable speed up, and you're getting a faster time to solution without wasting too much resource. If you really want to push it, 8 cores is doing well, but by the time you're up to 16 cores, you're at 43% efficiency. So you're spending, over half the time sort of is just wasted in some sense, rather than doing useful calculations or being that far away from the perfect speed up. Right. So this is the metric that allows you to start to make decisions about where the right place, what the right number of cores in this case, or what the right input parameter choice, or whatever it is you're measuring, starts to make a difference. You can start to make decisions based on this metric, quantifiable metric. Okay, so as it says here, anything less than 70% power efficiency is considered poor scaling, and less than 60% power efficiency is generally not considered a reasonable use of a terminal for workflow production. Now, of course, if time to solution is really, really critical for you, say, there's an urgent request for data. Now that could be, somebody's querying something on a paper you've written. That counts as urgent. But it may also be people like to do urgent computing, to support, particularly in the future, support analysis of natural disasters or medical procedures or responses to global pandemics. Then the time to solution becomes the critical thing, right? And you're willing to throw away more, you're willing to throw less efficient use of resources at it to get a quicker time to solution. So it really does depend on the context and what you're doing, and you have to be careful of saying something should never be done. In this case, once you get up to 64 cores, actually, you can look at you can also in these things look at the time to solution. This is 0.32 seconds once you get to 64 cores, and it doesn't actually get any much better than that beyond then. You know, so there's actually no point, even though it is getting slightly faster, but there's no point going much further than that because you're not actually getting it any faster anyway. Okay. So we've finally got to a stage where we've got a metric that we can make a decision about our parallel scaling here for this application, about how we decide what the right place, the right number of cores to use is for our production runs, so we can make good use of our HPC resources going forward. What I wanted to talk about a bit here is just to get this is less sort of the number crunching stuff and the analysis we've been doing, but give you an idea of some sort of more formal measurements of parallel scaling and what the problems are here and why the overall scaling curve for this particular case looks so bad, you know, that you can't get to very many cores. And with this, even though the calculation, if we look back at the calculation part of it, let's look at the calculation efficiency. It's actually got useful efficiency for the actual calculation bit up to 128 cores. And you could even argue that it's scaling reasonably. It's doing okay up to 256 cores. It's not great, but, you know, it's still in some sense maybe on the edge of usable performance. Okay, so there's something going on here, which we talked about, and we talked about it was the I/O, but let's see why that is. So before we start that discussion, let's talk about HPC scaling is usually referred to in two terms, either strong scaling or weak scaling. And it's important when you're talking about interpreting this data, you know which one you're thinking about. In stronger scaling studies, the total problem size stays the same as the amount of resource, or cores in this case, increases. And in weak scaling, the problem size increases at the same rate as the amount of HPC resource, keeping the amount of work per resource the same. In the image sharpening case we've been looking at, we have not been changing the size of the input data. So this is a strong scaling problem. Okay, the amount of data, the total amount of data stays the same. We increase the number of cores, the amount of work per core generally decreases as the number of cores increases. In general, in most cases, strong scaling is more useful. It's a more useful phenomenon, but it is more difficult to achieve in practice. Okay. You could think about how would you use the image sharpening example to look at the weak scaling performance of this application. What would you have to change about the way we're running the program to do this? Has anybody got any ideas? Why? Something like that. Given I've only just introduced the concept of weak scaling, so you're asking a bit much, but you know, how could we change how we run this to explore the weak scaling properties of the sharpening code? Increase the output size. That would be a consequence of increasing looking at weak scaling, yes, but it's not about it. Yeah, increase the input size of core count you're getting. So that's correct, right? So we could use a bigger image. So if we had an image that we could scale up, or actually we could just replicate the image we have in a number of dimensions, then we could keep the amount of work per core constant. Okay, so we could investigate how well this program scales as you did that and the weak scaling more. We're not actually going to do that. We don't have time in this course, but you could do that. But it's important to know when you're looking at things, which of these two things you're looking at. Generally, people using HPC, usually if they're using software packages, a standard, they're almost always looking at strong scaling. You know, you're generally looking at, I've got this problem, and how many, you know, how much resource can I throw at it while it's still useful to work, to use HPC in the calculation, that amount of HPC resource for the calculation. Okay. So the limits of, so what's the purpose of weak scaling? So, but there are some cases where weak scaling matters. Okay. So typically, particularly for people in the areas of engineering or climate modeling, weak scaling is really important because what you're aiming for in those cases is often an increase in resolution. Okay, so your limiting factor in what you're doing, for example, in climate modeling is often the amount of resolution, the resolution you can use for a grid across the Earth or whichever subpart of the Earth you're looking at. Say the UK would be the UK weather. say you're doing weather forecasting. You want to increase that resolution, and the amount of computational power you have limits how much you can increase that resolution. But there might be some assumptions in the way the model's built into your program that are also limiting the scaling. Okay, and that is a weak scaling problem, because as you increase the resolution, you're increasing the amount of work, so you increase the cores at the same time, and you make use of more cores, but you may limit the weak scaling built into the application or the way you read data or something like that. So weak scaling is often most important. It often comes about when using codes that use some sort of mesh or grid to treat things, so things like climate models or computational fluid dynamics, or so I think some fusion codes behave in that way as well. Okay, so it is really, really important. Okay, sorry, I said there was often, but most researchers, rather than application developers, are generally have a fixed problem size that they're already working with. There's probably a few exceptions of people who are looking at what sort of models they can run on next generation computer systems and things like that, who are more, but there are exceptions, and weak scaling is still very important, a very important concept, and very powerful, very, very powerful. And what you tend to find is the codes that can weak scale as you increase the size of HPC systems. They tend to be the codes that may benefit most as time goes on. So one of the big benefits of the next generation of HPC systems will be for codes that are these grid-based codes that can move to exploit massive numbers of parallel processes or threads. So I just wanted to introduce some sorts of formal things about scaling and the limits of scaling. And they're well understood, and they've been understood for a long time, and they're captured in two different laws. One's called Amdahl's law, which applies to stronger scaling, and one called Gustafson's law, which applies to weak scaling. So Gene Amdahl said, it was back in the late 60s, right when, before even the modern era of HPC parallel computers, is that the performance improvements we gain by parallelization is limited by the proportion of the code which is serial. Okay, what does he mean by this? Well, we've seen the actual real example of this in our in what we're doing here, because this image sharpening example really strongly exhibits Amdahl's law. The reason this example stops scaling overall, even the calculation part scale well, is because there is a serial part of the code, which is the I/O. Okay, reading the input and writing the output. That is only done by one process within this code. It's a very simple code. The master process reads in the input, sends the work out to all the other processes. They do their work and then send all the data back, and then the data is written out in serial. So there's a serial fraction of the code, and the only bit of the code that's parallel is the actual calculation part. Okay, and you can calculate. I'm not going to do this in the window here, but I used VisiData to calculate the I/O, the amount of time taken for the I/O, by subtracting the calculation timing from the overall timing. Okay, the difference between those two is the time taken by the I/O, and you can see that it's pretty constant as we increase the number of processes, because it's serial, right? It doesn't benefit from having any more cores. The timing for it doesn't change. But what that means is that as the overall runtime drops, the fraction of the time of this runtime spent doing I/O increases, until here on 256 cores, almost 95% of the time in the program is spent reading in the data and writing out the data, and only 5 or 6% of the actual runtime of the program is spent in the parallel bit. Okay, so it's not surprising that when you start adding more cores, things don't get any faster. This is exactly analogous to the flying transatlantic example I showed at the start of our workflows. We've got to the stage where you're not increasing the speed, where increasing the speed of that component of this program is not affecting the overall performance anymore. Okay, and that is essentially what Amdahl's law says. So it's the serial part of the code that's limiting the scalability. Now, Amdahl said something specific about it. He said that the maximum speed up that you can achieve for any number of parallel resources, that's cores in our case, but it could be any sort of parallel resources, is given by 1 over alpha, where alpha is the fraction of serial work in our application. If we look at our example on one core, we can see that the fraction of the serial work, the I/O part, is actually about 8%, 0.08. So the maximum speed up we can ever achieve for this application is 1 over 0.08 or 12.5. It's only ever going to go 12.5 faster. That's the total limit. Like, no matter how many cores we throw at it, the maximum speed up we can get is 12.5. Okay, the actual maximum speed up we observe, if we go back to here, the overall speed up 9.93 is the best we get at 256 cores, is around 10. And this is because the parallel section doesn't parallelize perfectly at larger core counts due to these parallel overheads. We'll look at them in in the section later on this afternoon, when we're profiling. Okay, so you know you don't even achieve that perfect scaling for that bit. But what this should show you is that there's massive amounts of parallelization needed in parallel applications to make them a strong scale well, right? If we reduce the serial fraction of this code, speed up the I/O, so it's just 0.1%, it's just 1%, 0.01, then we'd be still limited to a maximum speed of 100, no matter how many cores we use. So on ARCHER2, there are 128 cores per node, and typical applications may use more than 1,000 cores, and some applications use tens of thousands, even hundreds of thousands of cores on the system. So you can start to imagine how much work has to go into parallelizing these applications, and how much of the application has to be parallelized well to be able to achieve any sort of reasonable speed up for these sorts of applications at this level of that level of parallelization. This is why, in some sense, this strong scaling is very, very hard to achieve in practice. Okay, and you have to work very hard to do it. How to evaluate? Jerry asks how to evaluate the serial fraction on software. So you can, if you know which bits are serial, like you do in this simple example, then you can do it the way we've sort of done it here. The other way you can do is, because you know Amdahl's law, you can work backwards from your observed. You can work from your observed speed up to actually calculate what the. You wouldn't be able to pull out what the serial fraction is, because some of the stuff's due to parallel overheads as well, and you have to be able to try and untangle those two things. But you can get some sort of idea of what sort of range the serial fraction lies in by working backwards from your observed speed ups. The other thing you can do is use profiling, which we'll cover in the section after next, or we'll have a brief look at section after next, which allows you to look inside the code, see which parts are taking up time, and spot where you might see some serial, where you might see the serial parts of your code. But it isn't that simple. It isn't super simple. If you look at things like MPI code and things like that, you could also do some sort of static code analysis to see how much time the code is spent on one process. It's usually the main process, the process 0, that does the serial work, because of the way people tend to write MPI codes. So you can look at that and do some source code analysis. But it's not a trivial thing to work out if you don't already know the code. Okay, let's have a quick chat about. I'll just quickly cover Gustafson's law, which is the equivalent for weak scaling. Where the size of the application increases here as you increase the amount of HPC resource. The serial component doesn't dominate in the same way, obviously. So the formal statement of Gustafson's law is, if you've got a certain number of cores or HPC resource and an application with a serial fraction alpha, the scaling, assuming no power overheads, is given by P minus alpha P minus 1. And you can work out what that means for different things, but generally, for example, we talked about an application before in strong scaling with a serial fraction of about 1%, leading to a maximum potential speed up of 100. If you look at that from a weak scaling perspective, then you get towards a maximum speed up on 1,024 cores, or 8 nodes of ARCHER2, of close to 1,024. It's 1,013.77, and this keeps increasing, and you'll be closer to the perfect potential speed up as you keep going off. So there's much more potential for easy scaling with codes where you're looking at problems that are weak scaled. Okay. So, and if you contrast this to the limits for the strong scaling via Amdahl's law for a similar serial fraction code, you can see why good strong scaling is much harder to achieve, right, than it is with weak scaling. So, and this sort of final bit here is a bit matches onto the question Julie asked. You know, given the better, it's a sort of from the other side actually that Julie, rather than the way you asked it. It's the other way around. Is, you know, given the best prospects for scaling applications using a weak scaling approach, why not do this all the time? You know, why not make everything a weak scaling problem, right? And then everything becomes easier. Well, there's a number of different reasons for that. One of them might be, you know, if we increase the problem size, it's got no relevance to the work we're doing. You know, it may not gain you more insight, right? You could potentially, you may think, you know, model a whole aircraft engine at the atomistic scale, but does that give you any scientific insight? Possibly not. Okay, and so the increased problem size might not actually be relevant to the research you want to do. You know, sometimes our time's better used running multiple copies of smaller systems rather than fewer large calculations, and that's one way of getting around this strong scaling issue. If you think about what I can do in parallel, you know, if I've got to run lots of calculations, how can I use that? Because that would give you perfect weak scaling in some sense. It's running things in parallel in that way. And there's no scope for increasing the problem size, right? You're just at the physical limits, then there's no point going any further. So weak scaling is generally less useful, but it is important in particular cases. But it is much easier to achieve good scaling with the weak scaling than it is with strong scaling. Okay, so that a little detour into sort of formal parallel scaling measures ends this section on the analysis for the moment. So hopefully that's giving you an idea of how you take your benchmarking data, which you collected mostly before launch, and then use it in some sort of analysis that allows you to make some sort of useful decisions on it about how you want to use your HPC time, or essentially apply for HPC time in the future. So the next section is quite a quick one. Hopefully, we're going to look at how to automate running the benchmarks. Because actually, a lot of we already have a script for automating turning our data into a CSV, which we can manipulate and do some analysis on. There was a bit of a manual overhead. It was actually running all the different benchmarking calculations, and that was for a very small simple case. So we're going to look in the next section about how you might go ahead about automating that, and then there's a final section introducing profiling and what that might mean and how that works with benchmarking and how that helps us with performance before we finish off the day. So that's just about an hour and a quarter of time left. So what I think there was supposed to be this section which is quite short, and then a break. But actually, given it's quarter to 3 right now, I think it would actually make more sense to go for a 15-minute break now, give people a chance to have a cup of tea, have a cup of coffee, stretch their legs for a moment, and then we'll come back and do the last two sections and finish off the course. If anybody has any questions about stuff we've covered right now, then please feel free to ask me. I'll stay here for the moment before sneaking off to get a cup of tea for 5 minutes, for a couple of minutes before we start again. But please feel free to go away, get yourself a bit of refreshment, and we'll start back at 3 o'clock and go through the last two sections of the course. But if anything's not clear to you or you've got any questions, please just ask. I'll just give it another minute. There's still a few people missing. Okay, let's get started anyway then. Yeah, I know Yevgeny has been in and out anyway of the session, so he may not be back right away anyway. Okay, so we've now been able to collect data and analyze it, as I said, and be able to get to a stage where we can make decisions based on it. Now, the final sort of step in the benchmarking side of things anyway is to try and make it a bit easier for us to collect data. The moment, or when we ran the benchmark collection before, although this was quite a simple example, it was still relatively manual and tedious to do the separate runs. And we can try and get over this by automating and building some scripts to help us do this, or using some sort of automation to help us do this anyway. But it's not just convenience that automation helps with. In addition to reducing that manual work, it also gives us some other benefits by using an automated approach. You can make the collection of the data more systematic across the different parameters. There's no chance of a mistype, or there's less chance of a mistype getting the wrong file name or forgetting to include some data that we needed and having to redo the benchmarks again. And it allows us to more easily survey where there are gaps in our benchmarking data. You know, we've got lots of parameters varying. It's quite hard sometimes to make sure manually that you've covered all the parameter space that you wanted to cover. It can make the result of the details more consistent. It can simplify the automation of analysis because you don't have lots of things stored in different formats from when you did different runs at different times. And it can make it easier to rerun the benchmarking in the future on the same or different systems. You know, some time spent automating now means that when you get access to a new system, you can more quickly get up and running, quickly run your benchmark set, get your decision metrics, and decide how to best use the resources on the new system you've got access to. Or something changes on the system where things aren't working quite as well as you thought they were, you can rerun the benchmarking and compare it to what you had before. And it might give you more information about where the differences lie or what's gone wrong or what's changed on that system. So the automation has a lot of benefits, and if you're going to be doing much more than simple basic benchmarking, it's usually worth the time investing in automating in some ways. Okay, so there are different approaches to automation as well, and it depends on what you want to do and what you're familiar with, how you actually want to do it. You know, you could write some custom scripts yourself for this particular benchmark problem, benchmark this particular application, which may be useful and is generally quite quick and lightweight and low overhead way to go. Those scripts could be written in Perl, Python, Bash, whatever you're most familiar with and whatever you're most comfortable with is usually the right choice, because learning a new tool, though interesting, may take more time than you want for what you're going to do. But there are also some sort of standard frameworks out there that we're not going to cover in any detail at all in this lesson. It's too much, you know, there are lessons in themselves on how to use these frameworks. But if you're going to be doing lots of benchmarking over a lot of time, then it's definitely worth taking a look at such frameworks and putting in the work to integrate with them, because you'll reap the benefits going forward if you're doing a lot of benchmarking. You know, one of the things we're doing Hpc at the moment is building a lot of our benchmarks into the reframe framework so that we can reuse them across different systems and monitor performance across different systems in a simple way and allow different teams to use benchmarks in different ways. So it depends a bit on what you're doing. What we're going to do here with the sharpened benchmarking as just an example of how you might go about things. It's going to say this is the perfect way, the right way, the ideal way to do it. It's an example of how you might go about it. Is to use some bash scripts to help us automate what we want to do. And the first thing, as always, is to stop and think what you want and what you want to collect. What data do we need to capture from the runs that's not captured in the output of the application itself? The things we're varying are the number of cores, the run number at this data point. The things that we need to capture, they're not on the application output, at the moment anyway, from what we've seen from Sharpen, are the date and time of this run and the run number at this data point. The date and time of the run can be important, particularly if you run into problems. You'll be able to say to the service desk, oh, I ran this job at this time. It may be that that information is available by just capturing the job ID that it ran under in a batch submission system, because that often has the date and time associated with it in some way. But you may want to do it more explicitly, which is like we're going to do here. We've already seen how we used srun directly to run these benchmarks, but in this case, we're going to use job submission scripts to run the benchmarks. It's not strictly needed here. We can continue to run srun, but it should demonstrate an approach that's more flexible for maybe for what you potentially want to use for your own applications than you could do with using srun directly. So the first step here is to write a template job submission script. Okay, so this is a job submission script that you might use on ARCHER2 to replicate what we did with the srun commands. There is an exercise here to do this, but what I'm going to do in the interest of time a bit is I'm going to just show you the solution to this and walk through it a bit, this one, and walk through it a bit and say why we're going to use it for our starting point. So because it's reasonably complicated, what we're going to do is we've got a job submission script that does a similar thing to what we do with the srun. Some of the options we were using are captured up here in sbatch specifications, and some of the things we did interactively on the command line, like loading the training Sharpen module, have to be included in the job submission script. And then finally, with our srun command, the outputs to our output thing. And here we've got run 1, because this is just the first run. We're using this environment variable, slurm end tasks, which captures the number of cores that are being used in total, that's set automatically by the job script, rather than us having to change it each time. The other differences are we have to load this Hpc job env module as the first module loaded to be able to get the right sort of calculation environment on the job script. Everything else is the same, apart from the fact that we gave the job a name here. So that's our baseline job submission script. But it's not quite what we need for automation, because some of the things in this job submission script are going to have to vary each time we want to run a different case. And the things that are going to have to vary are the number of tasks per node in the first instance. So this is just to run the single core example, but actually we might want to run 2 cores, 4 cores, 8 cores, up to a whole node. We'll worry about the multi-node stuff later on, but let's just worry about running a single node one at the moment. Okay, and the other thing that needs to vary is the run number identifier. This is just for run number 1, and we're going to do 3 separate runs at least here, like we did before. And as I mentioned before, we want to maybe capture the date and the time of the run as well. So we want to write a version of this job script that allows those values to change programmatically, a parameterized version. Okay, so we're going to change the sbatch number, and we're going to capture the date and time of the run in some sort of thing in a timestamp. For this, we're going to use this command date plus %s. That gives us the number of seconds since the 1st of January 1970. So if I just run this on the command line on ARCHER2, it returns this number, and every second increases, that number increases. So there you go. So there are a few seconds between what I said before and what I said now. Looks like 7 seconds. So that number's changed. Okay, and this syntax, I don't know if you've seen it before in Bash. So Alessandra's asking, can we use CPUs per node rather than tasks per node? I'd have to check the Slurm documentation to see if CPUs per node was an allowed option in Slurm. I'm not sure that it is. I think tasks per node is the right thing to use in Slurm. It will differ depending on which batch submission script you're using, what the specification is. But if you use systems with Slurm with CPUs per node, it might work on ARCHER2. I'd have to, like I say, I don't know off the top of my head whether that's a valid option for this on ARCHER2. So if you've not seen this bash syntax before, this set this variable, the value equal to whatever comes out of this command. That's what the braces. You may have seen it also written with backticks, is the old-fashioned way to write it. So timestamp equals date plus %s in backticks. And that's the sort of older syntax for capturing the output for a command, but this is the recommended one now. One thing to remember when you're bash scripting is that you can't have any spaces on either side of the equals. Otherwise, it's not valid bash. Okay, so let's create a bash script version of our job submission script that allows us to specify these values. So here it is here. So I'm going to go up a directory. I'm going to create a new automated directory. dir sharpen bench auto to keep this stuff in. Okay, and I'm going to copy across this bash script in a minute into a file called run benchmark.shell. But let me walk through it first and say what the different bits do. Okay, and when we want to run this script, we'll issue the command bash, the name of the script, and then the two arguments here. The two arguments are then captured into these variables. The first argument is the number of cores, and the second argument is the number of repeat runs we want to do. Okay, this represented by these special values $1 and $2, the first and second arguments to the script. Then we use this thing which is called, rather horribly in bash, a here document. And this says, run the sbatch command, which is the command to submit batch scripts rather than just srun directly. It submits batch scripts to Slurm, and pass into it everything you see until you reach the string EOF. So EOF's down here at the bottom. So everything between EOF here and EOF here is passed into the sbatch command. And you can see it's our template job submission script, just about, but some things have changed. Things that have changed are we replace tasks per nodes with the value of n cores, which is captured as argument 1. Okay. And then instead of just doing srun once, we're going to srun n runs time. Okay, one at a time. We're going to run them in sequence. So this is a loop that goes for this variable I run in a sequence of 1 to number of runs, which is our second argument there. We capture the timestamp, and then we issue the srun command, which just is our normal one, and then outputs into the file. We've got srun n tasks, as we did before, number of cores. The run is the value of I run, which is varying from 1 to number of runs. And then finally at the end here we have time, we use timestamp. Now you can see, one of the confusing things here you can see is there's two different ways we've used bash variables here. There's these ones that showed up in colors. These ones are being captured from when we run the script. And then there's these other ones that have been escaped by having a backslash put in front of them. And these ones are not interpreted when we run the sbatch. They're interpreted in the job script when it runs rather than at the time it's submitted. Okay, so these are two slightly different uses of bash variables. Sorry, here's a question here. Let me just double check that. Sorry, I'm just getting to the chat so I can see the question. So, Helen asked if we looked at the job ID for one set of 3 runs, would it count as 1 submission or 3? Okay, it will only count as 1 submission in this case because each job submission repeats the calculation 3 times. You could do it the other way around and submit it 3 times instead. Okay, it depends what suits for your for what you want to do. In this case, they're short enough that you can just run 3 of them in the same job submission script straight after each other. Okay. Michael's checked sbatch and tasks per node is the only one. CPUs. So CPUs per node, it doesn't exist as an option. Yeah. And there's CPUs per task, but that's something different. Yeah, so depending on how you want, there are different ways to break it up, right? So you could make every benchmark run a separate job submission script, in which case you would submit 3 different copies of the script to do your 3 different runs, or you can use a loop within a job submission script to run it 3 times, for example, in this case. Maybe it'd be clearer if I didn't have the loop within the script here. I might think about that for the next one of the course. That would make it maybe a little less confusing here. But what we're doing is we're running the same benchmark 3 times, one after the other. Yeah. Okay. So when this runs, it will run 3 times, 1 to 3. It will create a timestamp and output the data. And then to run 3 copies of the benchmark on a single core, use this one because the first argument is the number of cores and the second argument is the number of things to copy. And you get submitted batch job because it's submit one batch job. Okay. So let's save this script. So I'm just going to copy and paste this into the actual file on the system to make this easier to do. So I'm going to copy that, and then I'm going to save a file which was, so I called it run benchmark.shush, didn't I? Run. Okay, so that's our job script. So I could submit this. I could do, if I wanted to submit the one on one cores, I could do bash run benchmark one core, 3 copies. Off you go. And if we look in the queue, oops, might have finished already. Yeah, it's finished already. But if you look here, oh, something might have gone wrong because of the core. So something went wrong here. Okay, and we can see that because there's this core file appeared. It's still got the output files, but I looked in this slurm output file to see what had gone wrong. And what I'd actually forgotten to do when I'd created this new directory to run in is I'd forgotten to copy the input file across. Now it's created it already because Fortran's like that. But what I'd forgotten to do was copy the input file across. So I'm going to move all the files apart from that one, apart from my run one, and I'm going to copy the input data across from the other. Okay, so I need because I'm running in this directory, I need the input data copied in this directory. So let's try that again. So once more with feeling. It might have finished, it might be too quick for me. Oh no, it's still running there. Still running. And it's created 3 copies. There's no core this time. There's a sharpened PGM, so that's all looking good. It's finished. So what is this variable equivalent to QStat? It's SQ. Shows all the jobs in the queue. SQ minus U, and then your username, which is captured in the environment variable $user, shows just your jobs. Okay. And we should see that I have 3 copies. If I cat all of those files, there's 3 copies of the benchmark run on one core. Okay, so that's automated that bit. The bit we're now missing, of course, is how to submit automatically lots of these job submission scripts. So we can create another bash, very simple bash script to do that. So in this bash script, because it's very simple, we're just going to encode the different parameters, different core counts into the script itself, rather than create a separate file that contains that data. If you're doing something more sophisticated with multiple variables varying each time, you may want to create a file that actually holds different values of the things you're changing. But in this case, we're just going to hard code them. So I create a variable in bash that holds all the different core counts we want. I tell it how many repetitions I want for each core count, and then we loop over each of these values in turn for cores in the set of core counts. Then we call our run benchmark with the number of cores and the number of repetitions. Okay, I'm going to save this one in a script called launch benchmark.sh in the same directory here. Okay, so this is running on 1, 2, 4, 8, 16, 32, 64, and 1 to 8. Remember, we haven't got a version of this script that could do multiple nodes yet. Yeah, so Michael's put in a command there that lets you look at completed jobs as well, rather than just your running jobs. Number of repetitions for each core count is 3, and we loop at each of the core counts we've set in this variable and run that copy. So let me save that. What I am going to do is delete these benchmarks that I've already run for that I showed you already, because otherwise I'll get 6 copies at a single core. And I'm going to remove the slam thing in case someone goes wrong. So let's cat launch benchmark.sh. So we should be able to do bash launch benchmark.sh. Hopefully that's submitted 8 different jobs. And if I look in the queue, but just my jobs rather than seeing everybody's. Oh, they've almost finished already. They were very quick. Okay, and we can, remember, use grep before to check that they all have the right sort of data. Grep time started out. And you can see it's run all those copies. So what we've done with some very simple scripts is make it so we can issue one command to run all of our benchmarks. And what it's helped us with is we've now got a very consistent set of output file names that we can use for analysis. And if we wanted to rerun steps or do something different or change something and rerun them, it would be much easier now. We just update our automated scripts and do the rerun. And if you remember, we already had we already had a little program to help us extract the output from all these scripts, and that was sharpen perf.py, and we gave it the extension out. So I can do that. Oh, something's gone wrong in the sharpen perf.out. Oh. Do you know why that is? That is because of these slurm.out files that are causing the problem here, because they've got the extension.out as well. It's trying to read them. So let's remove the slurm ones. Okay, let's try that again. There we go. It worked better that time. Oh, it's sharpen data actually we used last time, wasn't it? That's better. Okay, so that gives us the CSV file and a set of data from running all those calculations in an automated way. Okay, so I hope that makes some sort of sense. There is a small exercise here for modifying the parameterized submission script to allow for multi-node runs. So we went up to 2 nodes for 256 cores. At the moment, that wouldn't be supported with our automated script. There's lots of different ways to do this. And the way we're proposing the solution is just adding a third argument. So as well as collecting the cores, we used to have n cores and n runs. Now we can collect number of nodes, number of cores per node, and number of runs. And then you could add that in, but the script's mostly the same. And I would extend it easily up to being able to run on multiple nodes. And then you just need to update the launch one as well to include the node counts that you wanted as well as the core counts. Does that make sense to people? I know I've gone through that quite quickly, but I do want to leave a bit of time to talk about the profiling because people were interested in a bit more detail, because people were interested in that earlier in the course. And the automation stuff here, you can go away and try it yourself. This material is all just going to stay there on the website. So this is something you can work through in more detail if you haven't quite followed it. And you could always ask questions about it at the follow-up session we have in a few weeks' time. And there's an hour-long session in a few weeks' time that for you to come back and ask questions if you want. Does anybody have any questions on that bash script automation example? You should worth bearing in mind that this isn't the way to do things. It's just an example of a potential way you could do something quite easily and quite quickly that would lead you to an automated setup. Okay, it's all quiet. I've either lost everybody with that or nobody has any questions. It could be either of those things, I think, because I did go through that quite quickly. The only thing I wanted to say at the end was, I said at the start of this little section that there was more complex frameworks available that people have built specifically for doing these sorts of things and for automating benchmarking, collection of data, and analyzing data. There's a few of them named here that we've come across and found useful. So I mentioned already Reframe, which is what we're using at the moment. It was developed by CSCS, which is the Swiss National Supercomputing Center. It's really a regression testing framework for HPC, but actually has a lot of powerful features that allow you to capture performance data and then analyze it over a period of time and see how it varies and things like that. It's a very useful thing. You generally write little Python scripts that say how to maybe compile or how to just run your application and what sorts of parameters you want to look at. For distributing runs in time, would you use Reframe? So yes, that's what we're going to do, Evgeny. So one of the things we're interested in is how the performance varies over time on the system and have a sort of continuous monitoring of performance, or monitoring every so often. So what we do is have the Reframe tests set up with performance encoded in them and the way to capture performance encoded in them. And then we'll set up a way of launching those on a regular or randomized time basis. I think actually a combination of those two things. So it'll be regular, but slightly randomized. So it's not always running at the same time each week or each day, because you want to measure the performance at different times in case you overlap with system processes or things like that. If you do everything at exactly the same time, you might get hit with that. So that could be done coarsely using a cron job. It could use some sort of CI framework. We haven't quite got as far as deciding exactly how we're going to launch them all the time. It doesn't provide the framework for doing that. So there's also Jube, which comes from the Jülich Computing Center in Germany, which is a very comprehensive benchmarking framework. It's quite a steep learning curve, but provides a lot of features. And then finally, Dakota, which is more than just about benchmarking. It allows you to automatically vary input parameters to jobs, for example, and understand how that affects the sensitivity of the output that you're getting. So, if you vary the energy cutoff for a calculation, what's the sensitivity to the actual results you get to that? It's a very useful thing. And, this sensitivity analysis are things that's used hugely in commercial engineering applications where they use CFD, because you have to be sure that you understand what's going on in your model. So you need to be able to vary the input parameters and understand what the sensitivity of the output is to that. And it's not something that's very widely used in certainly academic HPC use at the moment, but should be, I think. Dakota does that, but it could also be used for benchmarking, because they're two sides of the same coin, the sort of sensitivity analysis and benchmarking performance. So we've got half an hour left on the course. We've got one last session to do, which is just a very brief introduction to profiling. Hopefully what you see with the automation side of things is it can make things more easier to do, but also make your approach more rigorous and more systematic. And so it has a lot of benefits, and I really would recommend spending even a small amount of time writing some sort of simple automation of the sort of thing we've seen here if you're going to be doing any benchmarking, because it will help you keep your organized and help you when you want to rerun it, because you will want to rerun it at some point in the future, even when on different system or even on the same system. Okay. So let's move on to this final session about profiling. Performance changes as you increase the number of cores. There's some sorts of scaling. You can observe these things, but it doesn't generally give you much information about why the performance is changing or why the scaling, why a code isn't scaling. It's quite an indirect thing, and you can guess and you can infer, and people have even done things like you could do, you've got enough benchmarking data, you can do, and across different systems, you can start to statistically correlate performance against things like memory performance or CPU performance or floating point performance to try and get some idea for the underlying causes of variation seen, but you don't have that direct thing. So profiling is a complementary activity to benchmarking that can provide that sort of direct information and understanding of why an application is performing the way it is. The reason it's not used more generally is it's a bit more time consuming and difficult to do, and requires more analysis and thought. So most people, especially if they're using centrally installed packages that somebody else has installed, what you really want to do is do some benchmarking, some reasonably lightweight benchmarking to understand how best to use your resources for the type of calculations you're running, and stop there. But it may come to the time where you want to understand what the difference is and why something's not working, and because you think it should be, or because you need to provide evidence of why it's not working. So that's what profiling does. And a profiling uses a different program, a profiler, to probe into your HPC application while it's running and to gather statistics about how it runs. And then you can use those statistics to analyze the performance and understand what's going on. Okay. So what it tends to do is it probes the application, for example, to find out how much time spent in different parts of the application. It gathers statistics and data on how much memory is being used and what's happening in terms of I/O, in terms of writing and reading from and writing to files. Parallel statistics, often from MPI, but also OpenMP and other parallel approaches that people may use. And the differences across different parallel tasks in the program. So, if one parallel task is performing very differently to another one, to try and understand situations such as load imbalance, where one task has a lot of work to do and other tasks maybe have less work to do. In this workshop, in this sort of final half hour of the day, we don't really have time to go into profiling in any sort of real detail. I mean, that's a whole course in itself. Instead, what I was hoping to do here was to give you an idea of what information is available from profiling tools on HPC systems, just so you know what's there, and potentially that gives you ideas of how you might use it in the future, or what the potential is for it to be able to use in a system, on an HPC system to understand the performance. So what we're going to look at here is we're going to go back to Sharpen. We've already talked a lot about it and understood the scaling of the overall Sharpen application, which is limited by the serial I/O part. Okay, we understand why it's working. But when we saw when we use large core counts, that the calculation part of the application also starts to show issues with scaling. If you remember the plot we saw, comparing it to perfect scaling, I hope you can remember that it wasn't keeping up with the perfect scaling. Even the calculation part, without worrying about the I/O bit, it was turning over and not starting to follow the perfect scaling curve. So why is this? What is stopping the calculation part from scaling properly? We couldn't infer that from benchmarking and from our understanding of, oh, there's a serial bit of the code. Okay. And so what we're going to do is use the CRAPAT-like performance analysis tool on ARCHER2 to look at this and use the information it provides to try and understand a bit about what's happening here. There are other profiling tools out in the world. We're using CRAPAT-like because we're on a Cray system, and it's what we have provided on ARCHER2 to use. And it provides generally actually more information than many other profiling tools. But other profiling tools are available on different systems and will provide information that's similar. Some of the interfaces will look different and the amount of data it provides will be maybe slightly more or less. But the bits we're going to talk about here, in the gross statistics and the overall statistics, should be available in any profiling tool, parallel profiling tool that you use. Now, one of the problems we have is the Sharpen application is a toy case that runs in a very short amount of time. So for the profiling bit, I've had to hack around with it to rerun the calculation, to make sure it reruns the calculation artificially more times, so 100 times, rather than just the once. Otherwise, the profiler, because so much of the time ends up being spent in the I/O, that would just dominate the profile, and we wouldn't be able to investigate what's going on in the calculation part at all because it's a toy application. Generally, that's not a problem for most real HPC applications because you want to analyze the real performance. But so just to be aware that the binary we've created here with the profiling built in does something slightly different to the sharpens you've already been doing, and it reruns the calculation part lots more times to increase its weight within the profile so we can actually see what's going on. Okay. So in the same way as you've had access to all the sharpen things, there's a sharpen binary with the profiling built in. And this course doesn't have the time to go into how you would build in the profiling into your application so you can get this data, but it is available on the Archer documentation. So if I, and it's not particularly difficult overhead. It's on the ARCHER2 user documentation. In the user and best practice guide, there's a whole section on profiling. And the first bit is how to use CRAPAT Lite, which is exactly what we've done in this course here. So you could follow these steps within the documentation to replicate what we've done if you wanted to. What we're trying to do as the service on ARCHER2 is for each of the centrally installed software packages, we're going to try and provide binaries with the profile option built in so that everybody has access to be able to profile applications that are compiled already on the system if they want to, without having to do any work at all. They just have to substitute in the name of a different binary into their job submission script. We're not quite there yet with that, but that's our plan going forward. So if you remember, we've got the S1 opt, so we're going to run this binary, run the profiled binary on 64 cores. In fact, before I do that, I'm going to back out and I'm going to create another directory for this. So I don't get things mixed up and so it's easier to see. And this time I'm going to remember to copy in the fuzzy image before I do this. So sharpen bench. Okay, so I've got the input image there. So let's take this, and we're going to run it on 64 cores. Ntasper node 64. I'm going to run sharpen MPI profile.x and put the output in sharpen 64 core profile.dat. Let's try that, see what happens. Okay, so you see some slightly different output this time because it's using CRAPAT. So there's actually a bit here that tells you that it's using the profiler to run it. And you should see that it's run and some extra things have happened. We've created the file, the output file that we specified, but it's also created this extra thing here. We're not going to talk about that right now. We're just going to look at this file, the output file it's created. So let's have a look at that. I'm going to use cat. Have a look at that. Okay. Okay, so there's a lot of output there actually. So I'm going to scroll right back up to the top of this, and you can see this is the normal output from the Sharpen program that we're used to seeing. We've seen all the way through the course. It tells us about the image. It tells us it's starting the calculation, and it tells us it's written the output. There's this extra nrep 100, just tells us doing 100 copies of the calculation. So something slightly weird in that I would have expected this to show multiple cores here. I think that's slightly odd, but there we go. Let's just keep it like that for the moment and have a look at the profile. Okay, so but below the output that we had before is the output from CRAPAT Lite. So if we scroll down, it says CRAPAT Lite performance statistics. And we're going to walk our way through this and try and see what's in here. There's only a few bits that are interested. It's got lots of data, but there are a few bits that are interesting to us. Firstly, there's let's go down to this first table here. This table indicates what percentage of time from the application is spent in different routines within the program. Okay, and I'm not interested particularly in the lower level stuff. It's these top level headings here that I'm interested in the first instance. That's user, etc, and MPI. And actually, I'm not interested in the difference between user and etc either. What I want to know is what percentage of time is spent in MPI. That is the amount of, there are the parallel overheads for using MPI for this calculation, for parallelizing this calculation. Okay, so of the total runtime, 5.6% of it is spent in MPI routines. So that's time spent not actually doing calculations, but time spent passing messages between the different parallel processes that are needed to implement the parallel algorithm. Okay, so that's not calculation time, that's parallel overhead time. Okay, so that's useful to know. That's only a small amount of time, 6% or so spent out of the total runtime. That sounds pretty good, right, in terms of parallel overhead. If we keep scrolling down, there's some more detailed information about routines. I'm going to skip that. There's memory bandwidth, which I'm going to skip as well. It's not particularly interesting for us at the moment. It does tell you how much energy and power your job used, which may be interesting to you. Some people are now interested in how much power their applications are using. But then it comes to file statistics, which I am interested in. One thing I said earlier was you'd be able to see that the I/O was serial within the profile, and you can. Right, so this is file input, and it's reading in from fuzzy PGM, and you can see the number of reader ranks is 1. That means it's serial input. And here we write out to sharpen PGM, that's the output data, and again you can see the number of writer ranks is 1. So this data is confirming what we sort of knew already, that the I/O is completely serial. There's these two other bits here, which it doesn't have. We do write some output to standard out. That's this file we're looking at, and that is parallel I/O in the way it's implemented at the moment. Okay. And the final thing I want to show you in here, we go back up to the top of where the CRAPAT data is. It tells you about the high memory high watermark. That's how much memory your application is using in total. This is one of the reasons we want to make the profiling information version of the executables available to people, is that people quite often have memory on HPC systems. And it's useful to know how much memory that the application is actually trying to use, and if you can provide people a simple way to gather that data by running a profiled executable, then we can gather statistics on how much memory each process is using and what the memory high watermark looks like. You can see here that this one is actually using very small amounts of data, only 5 gigabytes in total, or so 5 gigabytes or so. That's 5,000 megabytes. Okay, so there's a lot of data here, but actually the 3 things you generally want to look at first when you come to look at any sort of profiling tool and any sort of profile is what percentage of time is spent in parallel routines. What is the memory high watermark and the memory usage? What is the I/O usage? Okay, you may have more complicated questions depending on what you're actually doing and why you're profiling, but in general profiling, they're the first 3 things you look at. And actually, what this is telling us in isolation is sort of interesting, but not very useful. The useful bit comes when you rerun this calculation on a different number of cores. So now, let's go and profile it on 256 cores instead. Okay, so we did this run before. This was the 64 core one. So I'm going to take it to 256 cores. And I'm going to have 128 cores per node and 2 nodes. Okay, let's run that one. Hopefully it should tell us it's using CRAPAT again. Okay, that one's finished as well. So let's do the same again. You can see it's creating all of these profile files, but anyway, I'm not interested in that at the moment. Okay, so this is the output from that one as well. So there we go. So there's our usual fuzzy output. And if we scroll down this time, so the thing I'm really interested in is it's not, it's starting to not scale so well. So if you remember from when we looked at 64 cores, the amount of time spent in MPI was 5.6%, about 6%. Now the amount of parallel overheads, the amount of time spent passing messages is 26% of the whole runtime of the application. Okay, so what this is telling us now is, well, maybe you could have guessed this one without doing the profile, but the reason that the calculation part is not scaling is due to these parallel overheads. So as you scale up and use more cores, you start passing more, you're passing more and more messages around as part of parallelizing the algorithm. Okay, and so you're spending more and more time in MPI passing messages, and that time is dead time in terms of calculation. You're not doing useful calculation work, so that moves you further away from the perfect scaling that you'd want to see, because you're spending more time in parallel overheads. So you can see that we went from 6% roughly to 26%. So that's like a fourfold increase in parallel overheads when you went from 64 cores to 256 cores. Okay, so that actually matches quite closely to 256 divided by 4 is 64. So it seems to be scaling linearly. The amount of message passing at parallel overhead seems to scale linearly with the amount of the number of cores you're using, or the number of MPI tasks you're using in this case. Okay, so that's the sort of information that profiling, even very basic profiling. We haven't looked in any detail here at these statistics really. We've just looked at the amount of percentage of time spent in MPI, but we're already able to infer, how the parallel overheads increase as you increase the MPI task count, and where the lack of scale, where there's problems with scaling are coming from in this calculation, just by looking at the amount of MPI time here. And you could also see, actually, if we look at the high memory, you can see it's gone up as well. So the more the more tasks we're using, the more memory load we're creating as well for our application. So you could start to extrapolate that out. 2 points obviously aren't enough for extrapolation. We need some more data to see whether it's linear or curved, or what the dependency is. But you could maybe start to think about, if I was scaling out, and even if my calculation was scaling really well, at what point am I going to hit to memory available per process or per node? How far could I actually push this before I'm going to start running into memory problems? These are the sort of things where even simple profiling can help you think about how your application's using resources. So what I wanted to show you here was not in detail how to do profiling and all that sort of thing. Like I say, that's a course in itself, and actually a course, there are courses running later on ARCHER2 that cover the use of profilers in that advanced way. But I'm hoping what I've given you an idea of is what sort of information you can get from a profiler, and how you could potentially use that information to help you, not as somebody who's developing code or trying to implement new algorithms or things like that, but just to support your usage of an HPC system and help you understand, how far you can scale, when you might start running out of memory, and those sorts of issues. Really, profiling is a huge topic. We've only scraped the surface of this sort of the information available on how it can be used. There are other courses that can help you out, and other online resources and tutorials that can help you out with profiling if you want to go in more depth on that sort of thing. So I realized that I've been talking away. I missed a question from Jovi about modifying template scripts using sed rather than here document and bash variables. So sed is right. Like I said before, it wasn't the automation I talked about wasn't meant to be say this is the right way of doing it, or this is even the best way of doing it. Different people have different skills and will do things in different ways. And one of the problems with Unix Linux is there's a million different ways to do anything, and it really depends on your experience. If you're comfortable with sed and using sed, then that is more than appropriate, right? If you can use SED succinctly to do things, that's just great, right? Use it. SED is definitely a useful tool and could be used for this sort of thing. The challenge I have with SED, with trying to put it in a course here, was where I didn't know the level of everybody's expertise, is that SED tends to be a bit harder to explain, I find, than actually explicitly showing the script. And especially when you get into more complex regex replacements and things like that, it's a very dense way of expressing something quite complex, and it becomes more difficult to explain, which is why I've stepped away from SED here. But you could absolutely do this using SED, and that would not be considered in any way bad, poor, or anything like that. So, does anybody have any questions on profiling? I know it was a sort of a whirlwind tour of profiling. The thing to say right at the start of the course as well, of course, is that the accounts you have for this course that you're going from this project are going to be valid for another 3 weeks at least after this course finishes. So you can use that time to use the system, explore the performance, explore the tools. If there's any of the course material you want to go back through and have a look at and have a go again and play around with, you've got time to do that with the accounts you've got. The only thing you won't be able to do is use the reservation, because that finishes at the end of today. But you can submit jobs in a normal way as described in the ARCHER2 documentation, and you can continue to use the resources in this project, in this training project, for a lot longer. Your accounts don't go away at the end of today, because we want to give people a chance to try out things who wouldn't otherwise have access to the system. Okay, so please feel free to try things out. So we're almost at the end. I have a few small things I want to say right at the end, but I'll just give it a moment in case anybody has any more questions on the profiling, to give them a chance to ask them. No? Okay. Fine. So I will move on to just this last little bit, which only takes a couple of minutes anyway, because we're right at the end of the course now. So this session sort of speculatively titled "Where Next." So it's region. There's hardly anything here at all at the moment. So what I just wanted to say was, there's a lot of, from where you go next from here, from this course, is up to you and up to your requirements. What I hope with this course is not that I've answered all of your questions or benchmarking or giving you the exact right way to go about benchmarking and understanding the performance of your work, your research workflow, and particularly in the context of HPC and the applications used on HPC systems. That was not the aim here, was to give you all the answers. The aim here was to give you enough useful information that you can come up with a useful strategy for yourself, and to give you maybe food for thought to how you might start to think about those sorts of things. Because there's no way that a one-day course like this can answer the questions for all the potential different research scenarios and different uses of HPC that people possibly could have. But hopefully it's giving you enough information to start thinking about them in a useful way. In terms of further training that might be useful after this course, there's lots of other stuff from ARCHER2, that's freely available, and everything's going to be online for the foreseeable future anyway, at the moment, with the situation around the world and in the UK. So there's a couple of courses. There's the package use. There are various package use on ARCHER2 courses that cover different software packages that are commonly used on the system. They're scheduled different times. For example, we've had LAMPS courses, a CP2K, and I think there's plans to do OpenRoom as well, and other packages. Some of them might be useful to you if they tie to the sort of packages you're going to be using in your area. There's also a performance analysis workshop, which you'll be running sometime in the future, which is the more advanced use of profiling tools. So that's analyzing code in depth and understanding what the profile is telling you and really optimizing. It's more aimed at developers rather than people who are using the applications. But if you are close to some code developers that are for the code you're using for the HPC system, there might be opportunities to tie the sorts of problems you're running into code developers and optimizing them and using them in the performance analysis workshop, where you get in-depth support from both Hpc and Cray and potentially AMD experts to optimize the performance of the code on the system. If you're continuing to use ARCHER2 for your research, there's lots of specific support out there for ARCHER2. There's the documentation, which is really quite comprehensive at the moment and is always being added to, and also gratefully accepts contributions from the wider user community. It's it's open source repository, the documentation source on GitHub repo, and people can issue pull requests against it if they've got something that's useful or interesting for other users of ARCHER2. So it's really meant to be a community effort to document the use of the system. There's the service desk where you can put in queries, ask any questions, technical, no matter whether you think they're silly questions, hard questions, they're there to help and they respond to any questions that people have. You can also, through the service desk, book a call back with an expert from EPCC to ask particular questions about what you're doing in your research workflow and your use of HPC. And we're happy to give you a call on whatever technologies you choose, Zoom, Teams, whatever, and talk to you about your use and help you out with either problems or just have a more general chat about how you might want to implement things more efficiently on the system and how you can get the best out of the system. So please do ask if you want to do that. I would say also, if you've got other questions around the use of HPC that maybe aren't ARCHER2 specific, or that we weren't able to help completely with, then you may also be able to help from your local research software engineer. Research software engineers are people with expertise in software engineering who help out researchers make the most of computational resources or software. If you're in the UK, there's a link there to a list of the UK RSE groups. You'll be able to find somebody local or somebody linked to the institution you're part of. And there are also international RSE groups for those of you who aren't in the UK. But actually, most RSEs, no matter where they're based, are always happy to try and field questions from people wherever they come from. Okay. So I have two final things I want to say right on the end. Two final points. One is that the feedback form is now live on the ARCHER2 website for this course. So if you go to ARCHER2, ACUK, and the training, you can find the course here. It probably won't be moved. It'll be moved away from upcoming training into the training materials repository soon. If you click on that page, there is a link here where you can provide feedback on the course. As I said at the start, this is a new course, and we put quite a lot of work into developing it so far, but we really want your feedback, both positive and negative, about the course to help us improve it going forward. And it definitely can be. I've learned a lot from teaching it today, and I've got some ideas already for what would be better. I would love to hear your thoughts about what could be made better in the course and how it could be made more useful in the future. The other thing I wanted to say, we can provide attendance certificates on request as well, and we will remind you about the feedback via email too. So you will get a prod about that as well. If you can't remember the link of where it's from, you'll get that via email. The other thing I want to say is we do have a follow-up session, an hour-long follow-up session. So we're aware that people go away, try stuff, and may think of questions that they would have liked to ask the instructors during the course, and then feel that they can't. Of course, you're always welcome to get in touch with us via. Sorry, it stopped. My internet connection seems to be slow, so it stopped sharing applications. I'll try and do that again in a minute. The other thing, so if you've forgotten, you can always get in touch with us via the service desk if you've got any questions. But we're going to run a session in a few weeks' time, actually at 2 o'clock UK time on the 15th of February. You'll get an email about that too, with the date and the link again on how to get access. And you're welcome to come and join us then. There's no pressure, it's entirely optional, you don't have to attend. But if you have questions or you want us to talk about a topic in more detail, then please come on to that session and we'll be there and happy to answer questions there as well. Okay. And finally, I just want to say thank you for coming along and taking the time. I know everybody's super busy, and I hope the course has been useful for you. And if it hasn't, please tell us why, and we'll do our best to improve it. But you know, thank you so much for coming along and your input during the day. I've really enjoyed teaching it, and I hope you managed to get something useful out of it too. I'm happy to, I'll stick around for a little while. If you've got any questions or anything like that, I'm happy to try and answer them. But if you need to leave, then the end of the course was scheduled for 4 o'clock. I understand that people need to leave, so please don't feel you need to hang around if you're not able to do that. And sorry, thank you so much to Michael and William. You're going to help us on the course today. It makes it so much easier. It makes it so much easier having them along to help people out as well as myself. And I really appreciate them taking the time to do that. They don't get paid for it. So thank you, everybody. Like I say, any more questions, I'll be trying to answer them.